Or ACT.
It depends on,
My face is probably like right.
and most every college will
What?
accept
Is it
either.
the same?
That's not how we learn Florida, but completely different.
Yeah,
No,
so
I think
the,
Because everyone who took the ACTs were going to state colleges or
Ours
community
was
colleges, and
yesterday.
people that took SAT or ACT or both of them.
he wasn't here for rehearsal.
No, but after what I heard about what happened yesterday, I'm not gonna miss
That
any
means
more.
any,
So you
just
just
so
don't
work.
work. No, yeah, like I was throwing up yesterday.
I mean, maybe
I'm
maybe
sorry.
if you let her know that, she'll be under more understanding, but
Doubt it.
she might. It might be worth a shot.
Maybe, I'm not, that's good. I just have like shooting migraine like all the way up here.
Oh my god.
It's
That
from,
sounds awful.
yeah, it's like from tension, it's like with my grandma just like having a stroke and stuff. And then like over the spring break, it was really, really like hard. And that's the only reason I have this headache.
That was the
Like,
answer,
it's
that's
hard,
good.
like, not kind of hurt, like, it was hard. And I was like, okay,
next break.
And I was like, thank you. And so you're
Yeah.
came over and then for me.
She just was.
She was just kind of upset.
Kramer was
Yeah.
going to, so
Kramer
she
was
No,
got
I
it.
know. It's like, if I was in fact, he's just strong. And I was like,
yeah, I know.
no, I was like, are you serious? No, I was like, go. If you don't feel it, go.
That could be part of my, like, general,
But she's on the positive, right?
oh, yeah.
Are you sore? Because I haven't heard that. Me too. I don't know, I was like, let's go.
Like, I normally do that all the time.
Today, yesterday was like my first day back, and I was just like, dead.
Okay. So, when we were talking last time, we discussed that every chemical reaction can be put into one of two categories: exothermic or endothermic. Exo meaning to the outside, therm meaning heat. This means heat is given off to the outside. And it may be counterintuitive when you look at a graph of energy over time with an exothermic reaction. But if heat is given off to the environment, then what you started with is more energetic than what you end with. Think about burning a log. What you start with has lots of energy. What you end with has very little, right? You start with a whole log, you end with a pile of ashes. The pile of ashes is relatively energyless compared to the whole log. Agreed? You guys are all okay with this? Good. So, when we talk about our reactants, we're talking about what we start with. When we talk about our products, we're talking about what we end with. And if you compare the energy of the reactants to the energy of the products, that difference is referred to as delta H. It's the change in enthalpy. You could think of it as the change in heat. And in the case of an exothermic reaction, the change in heat will be negative. What you end with will have less energy than what you started with. I gave an example yesterday. If you take carbon and burn it, that is an exothermic reaction. And in fact, the amount of heat that's given off is negative 94.05 kilocalories. Now, I need to be clear about what a calorie is because we've never, have we described what a calorie is? Doesn't look.
last semester, whatever.
Yeah, we did, yeah.
Calories and joules are related. So calorie, one way to think of it is a calorie is a unit of heat, energy. That's one way to think of it. That's a general way of thinking about it. Okay, a calorie is a unit of heat energy. What is a calorie specifically? A calorie, and this is good to know, bless you,
Let's see.
is the amount of heat required to raise the temperature of 1 gram of water by 1 degree Celsius. That's what a calorie is. The amount of heat required to raise the temperature of 1 gram of water by 1 degree Celsius. So, imagine, you wouldn't have much water if you only had a gram of water, but imagine you had a gram of water, a paperclip's weight worth of water. That's not much. And imagine the water was at, say, 15 degrees Celsius. That's about 60 degrees. A general rule with Celsius, should you ever find yourself in a part of the world where they measure temperature in Celsius, is double it and add 30, in case you were curious. It's a good way to work, double it and add 30. Technically, you're supposed to multiply by 95ths and add 32, but that's beside the point. Now, imagine you heated this water up, this small little 1 gram of water, up to 16 degrees Celsius, right? Big temperature change, right? 1 degree. Well, if you took that 1 degree, or that 1 gram of water and raised its temperature 1 degree Celsius, this would take 1 calorie of heat. Now, you guys have probably heard of calories before you ever stepped into a science class in middle school or high school, I imagine. You probably looked on a food label and talked about calories. Now, the food calorie is always has a capital C. You'll notice this whenever you look on a food label, the calorie always starts with a capital C. The capital C calorie, which is your dietary calorie, is 1 kilocalorie, lowercase. Kilo means 1,000, right? So that's just 1,000 lowercase calories. So let's think of a realistic example. What if you had a 1,000 grams of water? 1,000 grams of water is 1,000 milliliters of water. This is 1 liter of water. The water bottles that we sell at the front desk are not quite a liter, but there are water bottles slightly larger than that are exactly a liter. It's a commonly purchased size of bottled water, yeah. Right, the bottle that the bottled water is in. Anyways, imagine, this is just, you took this out of the fridge, right? So you took it out, and say the fridge is 5 degrees Celsius. That's probably about right, the double it and add 30, maybe 40 degrees. That's probably about the temperature of a fridge. Close to freezing, but not quite. And now when you put this water in your body, the water is going to heat up to the temperature of your body, I think, right? And your body's about 70 degrees, which double that and add 30, that's 20 degrees Celsius. So this is taking it out of the fridge, and this is putting the water in your body. It's still 1,000 grams of water, but now you've drank the water, it's in your body, and it comes up to your body temperature. Now, we can determine how many calories that would involve. Because we had 1,000 grams of water, and the water went up 15 degrees Celsius. So 1,000 grams times 15 degrees Celsius is going to tell you how many calories was required to bring the water up to temperature? And the answer is 15,000 lowercase calories, which is 15 uppercase calories. So, if you take the water out of the fridge and you drink a liter of it, you will use 15 calories to bring that water up to your body temperature. If you ever wanted to burn 15 calories, that's probably the simplest way to do it. Yeah, drink cold water. When the water brings up to your body temperature, you'll burn calories. Where would your body get the 15 calories from? From all of your organs doing the things that they do. And that's going to require some amount of heat energy to get from 5 degrees Celsius to 20 degrees Celsius, specifically 15 uppercase calories. So that's my dietary advice for the day. Yeah.
So when like the food label says like 100 calories, that means like to burn it off if it's, or?
Yeah, so 100 calories, if you have like the 100 calorie snack bar or something, right? 100 uppercase calories. This would be enough, well, this would be, let's say this, 100,000 lowercase calories. Which would be, there would be a number of ways to do this, but you could say that would be enough to bring 1,000 grams of water up 100 degrees Celsius. So the amount of energy in that food, should you say burn it, like you took the cereal bar and you threw it on the fire, the cereal bar would supply enough heat to raise 1,000 grams of water 100 degrees Celsius. So if you threw the cereal bar on the fire and you threw a 1,000-gram chunk of ice on the water, the cereal bar burning would take that 1,000-gram chunk of ice and take it from 0 C to 100 C and would boil it away. Yeah, isn't that kind of neat? So it's one way to think about all of the calories that you eat. If a normal diet is 2,000 calories, big calories, that's enough energy to take 1 gram of water up 2 million degrees C. Right? No, yeah, that would be a strange experiment to have 1 gram of water and have 2,000 calories of heat, because, well, that would, 2 million degrees C is a lot of change in temperature. It's probably an unrealistic, it's not an unrealistic scenario, it's just something you're not going to encounter very often, but yeah, that's what a 2,000 calorie diet would mean, because 2,000 calories is 2 million lowercase calories, which is where that number would come from. Mm-hmm.
What happens when you drink hot water?
So yeah, well, hot water would have the opposite effect in a sense, because if you put the water, say you drink a liter of water, that's 1,000 grams of water, and say it was practically boiling or close to it, like 80 degrees C, and then it has to cool down to 20 degrees C when it goes into your body, or else it's going to be causing like thermal damage to your organs as it would be going through your body. It's going to cool down, like when you drink the water, it's going to cool down to body temperature. This would be 1,000 grams of water times negative 60 degrees Celsius, which would be negative 60,000 calories, which would be negative 60 uppercase C calories. So it's going to require 60 calories of, or rather, you're going to gain 60 calories of heat energy in your body from that. And that would probably be the effect of like feeling warm whenever you would drink the warm liquid. The heat that would be given off would be 60 calories of heat that would be now in your body that wouldn't have been in there previously. So whenever we talk about, whenever you could see any reaction, I can bring up another example. This is what happens if anybody have a natural gas stove? Like the one that you have to like tick, 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 and then it lights? Yeah? Okay, so this would be the reaction that's occurring there. CH4 is methane, that's the natural gas that's going through the pipes. CH4 and 2 oxygens yields CO2 plus 2 H2Os. The delta H here is negative 212.79 kilocalories. So if you compare burning your pencil lead to burning your natural gas gives off more heat. Because burning your pencil lead gives off 94 kilocalories. This is actually, I should say, kilocalories per mole. And the natural gas gives off 212 kilocalories per mole. That's a lot more heat. Not unexpected. If you would imagine burning your pencil lead, it probably wouldn't give off as much heat as your natural gas stove. We could go one more here. C8H18. I didn't even have this equation memorized, but it's not important that it is really. It would be plus some amount of O2. I'm not sure what you could work through the coefficients. I'm going to leave the coefficients out. I mean, you could if you wanted to balance that equation. This guy, the delta H, which is how much heat is, the delta H is the change in heat between the initial reactants and the final products. So this is octane, that's what's in your gasoline. The number that's on the gas pump, like 87, 89, 93, is an octane rating. So it's approximately like the percentage of the gasoline that's the octane, approximately. It's more complicated than that. But at any rate, the delta H for octane is negative 1,302.7 kilocalories per mole. This is why your parents should have told you at one point in your life, don't mess with gasoline and fire. Hopefully. Because you light gasoline on fire, it gives off enormous heat. It's almost more than 6 times what your stove is able to give off. That's a lot. So if you piped, rather than piping natural gas through your lines in your house and coming out your stove, if you piped gasoline, you could heat up your water much, much quicker. The exhaust pipes on automobiles can get up to like 1,300 degrees C. And the water that's on your stove takes a heck of a long time just to get up to 200 degrees F, or 100 degrees C. So 100 degrees C, 1,300 degrees C. Not surprising, based on the amount of heat that's given off. Endothermic reactions are the exact opposite. So in an endothermic reaction, your reactants are low energy and your products are high energy. And when you compare those here, the delta H here will be positive. So if you're going to get an endothermic reaction going, you're going to have to give it a heck of a lot of energy for the reaction to occur. Whereas an exothermic reaction, it's going to be easier to get the reaction going. Why do I say that? Look at the amount of energy that's required to get over the hump. You can almost think of this like a roller coaster. Once you would get over the hump, you're going to be going down the hill, so to speak. And if you look at how much energy is required to get the reaction going, in the case of an exothermic reaction, there's just a little hump there. This is what's called the activation energy. And this is the amount of energy that's required to get a reaction going. We mentioned yesterday, Kramer brought up the example of an exothermic reaction being an atomic bomb. That's a very exothermic reaction. But, just to be clear, if the atomic bomb is just sitting here in the room, let's say, it's not going to go off unless we activate it. We're going to have to do something to get the reaction going. It's not a spontaneous reaction, or at least a well-designed atomic bomb shouldn't be spontaneous. Right? Now, endothermic reactions, look how much energy is required to get that reaction going. Because you're going to have to give the reactant's energy for them to become a higher energy product, that is a huge activation energy. The activation energy here is very large. Now, I suppose it is possible that there are reactions that are spontaneous reactions. And if a reaction was spontaneous, one of the things that would make it spontaneous is that it was exothermic. In other words, we're going downhill, we're not required to give it tons of energy, we're only required to give it a small amount of energy, and better yet, not only exothermic, but have no activation energy. If a reaction was endothermic, you are required to give the reactants energy, because you can't get from low energy reactants to high energy products without giving the substances energy. With an exothermic reaction, it's a downhill reaction. It's giving off energy. You don't have to give it any. And if there was no activation energy, there would be nothing required to get the reaction going. It would start on its own. So no activation energy means it starts on its own. An exothermic reaction would mean that there's no energy needed to give to the reactants. In fact, you're giving off energy. So in the case where you had an exothermic reaction with no activation energy, that would be one that would happen spontaneously. You would have to do nothing to make that reaction go. Example would be dropping Alka-Seltzer into water. You don't have to heat it up. There's no activation energy to get it started. You literally just drop the pills inside the water and they start fizzing and bubbling. That would be a spontaneous reaction. So we can put that down there. Alka-Seltzer. You guys know what that stuff is? Maybe you've seen a commercial. Say what? Yeah, oh, what a relief it is, yeah. Plop, plop, fizz, fizz, oh, what a relief it is.
Like that is your stomach.
It's it's supposed to help with like a stomach ache. You drop these little like chalky tablets into water and they start bubbling and dissolving. And then whatever it turns the water into is something that's supposed to be soothing to an upset stomach. Well, how it works, I really have no idea, but I just know that it works, and whenever you drop the Alka-Seltzer into water, it does it automatically. The reaction happens spontaneously, there's nothing you have to do. Again, if an atomic bomb was like this, that would be awful, right?
Technically, though, you have to put it in the water and
Yeah, so in a sense, you kind of have to like get the reactants close to each other. So that actually brings up an interesting point. And that's relating to kinematics, because we talked about this word yesterday. Kinematics is all about movement, motion, and whatnot. So if, let's imagine, for example, we had a reaction like this. Now, don't think of B's as borons and C's as carbons, just think substance A, substance B, mixed together and form substance C and substance D. Now, to be sure, to make this reaction happen, substance A must interact with substance B for the reaction to occur. I think that makes perfect sense. That should make perfect sense. Because if A and B interact to form C and D, well then A and B are going to have to interact in order for C and D to form. If you kept A and B separate, there would be no interaction and thus no reaction. But if you get A and B interacting with one another, you would form C and D. Now, can you think of anything that you could do to substances A and B when you have them interacting with each other that would increase the number of interactions? What could we do when we get substance A and B together to make them interact more vigorously, to make them interact more often? Yeah, heat them up, okay. So one thing to think about is heat affects motion of the particles, right? The faster you heat the particle up, the more that particle starts moving. And if the particle is moving faster, you could say this. So if you increase the heat, you're going to increase the particle motion, and as a result, you're going to increase the interaction of A and B. And what's going to happen if you increase the interaction of A and B? What's that? Yeah, you're gonna make C and D more quickly. One way to increase the rate of a reaction would be to heat it up. The faster you get the particles moving as a result of the heat, the more the particles are interacting, and the more you're making C and D. What else could you do besides heat? Because heat would be one thing that you could do. What else could you do to increase the interactions between the particles? Olivia?
If you like stir them.
Yeah, if you stir them together or shake them up. So if you stir or shake up the particles, this will also affect the motion. So we increase the stirring. We're going to increase the particle motion. We're going to increase the interaction of A and B. And as a result, we're going to make C and D more quickly. So that's a fact about kinematics. Again, the motion of the particles. So faster moving particles would be faster interacting particles. And faster interacting particles would be particles that would produce C and D more quickly. If A and B interact to form C and D, then the more A and B interact, the more quickly they interact, the more quickly you'll form C and D. Does that make sense? Seem reasonable, at least? So that's when it comes to kinematics, when it comes to getting the motion of the particles and thinking in terms of that. Yes, heat and stirring or shaking up the particles would be the two foolproof ways to increase the rate of a reaction. You increase the interactions, which increases the formation of the products. Okay. Now. Oh, we're out of time. We'll start next, or we'll start next.
I'm milking that.
I think we can cash out for that, right? Wouldn't that make sense to you? You're gonna hold on to it.
It doesn't matter, we're like,